All right, let's solve part B of this question. A little trickier. As you can see, we're given 3 lines to answer, which means it's going to be a little tricky, but that's fine. So let's take a look at this circuit. What's the first thing we notice? Well, it opens, right? The gate opens at 20 microseconds and the circuit changes, right? So we know at t 20 microseconds, something happens before, something happens after. That should be your first immediate sign that, hey, this is going to be piecewise and we need 2 different equations, right? So let's take a look at what happens before 20 microseconds. So before 20 microseconds, this gate is still closed, which is good. And we have the circuit, right? One thing you should hopefully immediately notice is that this is a parallel second order circuit, right? If you look at our cheat sheet, it looks just like this one if you just added in a current source, right? So we can use these equations. And actually, the first thing we have to find is whether it's overdamped, critically damped, or underdamped, right? And that depends on alpha and omega. So here's how we find those. These are the 2 equations we're going to use. And so yeah, let's just find those. And remember, it needs to be in this form if you're going to use those 2 equations. If it's not, you might have to mess around with the circuit a bit, like simplify it, Thevenin, whatever. But for us, it's already in this form, which is perfect. So what do we have? Well, we have alpha is equal to 1 over 2RC, right? What is that equal to? Well, that is just equal to 1 over 2 times 10 ohms times, what is it, 1 microfarad? I think so. Yeah, it is 1 microfarad. Okay, cool. Now you solve the math on this, and what you get is 50k seconds minus 1. All right, so that is our alpha. Now let's do our omega naught. All right, so how do we find this? Well, again, we have the equation provided to us, so we just plug that in. Square root of 25 microhenries times 1 microfarad, which is equal to 200k. That's negative 1. All right, now let's take a look at the 2 of these and compare them. What do we notice? Well, obviously, omega naught is greater than alpha, right? Pretty straightforward, which means we are going to be, what are we going to be? Let's check the cheat sheet, underdamped. All right, pretty straightforward. All right, now that we know we're underdamped, where do we go from here? Well, the first step is we got to find our solution in this form. We know this is going to be the natural form, right? Obviously, we're going to have to add on the forced, but for now, we just know that this is going to be our natural form. So how do we find that? Well, first what we need is this term right over here, right? The omega naught, or sorry, the omega d, and that's given to us in this equation. So let's just use that equation. Just get this out of the way. So what is this equal to? This is equal to the square root of omega naught squared minus alpha squared, right? Now what's that equal to? That's just equal to the square root of our 2 numbers from earlier. So 200k squared minus 50k squared. And what does that give us? That gives us this number, if you put it in your calculator, something like that. Okay, it's kind of a weird number. We could simplify, but I'm just going to leave it like that for now. Okay, so that's that number taken care of. Now, what else do we need? Well, we need B1 and B2. How do we find those? Well, in this year's exam, it didn't have it in the cheat sheet, but in the 2024 cheat sheet, we get this table right over here. I don't know if it's going to be in our cheat sheet for our exam, but hopefully it is. I'd say just keep these equations in your cheat sheet anyways, because this makes it easier, right? It tells you how to find, It tells you how to find these 2 constants pretty easily. So what do we know? Well, we know that D1, or B1, right? In this cheat sheet, it's D1, and the other one, it's B1, but it's the same thing, is equal to x0 minus x at infinity, right? And in our case, we're trying to find current. So we're trying to find this. Okay, so do we have those 2 values? Well, yeah, we do, right? If we go back to our first part, we have both of these right here, 0 and 10, right? So we can just go back and sub them in. So we know that our B, I'm going to leave it as B. It's B or D, they're interchangeable, all right? B is equal to 0 amps minus 10 amps, which is equal to negative 10 amps. All right, pretty straightforward. How do we find our other b? This one is going to be a little more tricky. As you can see, we need the derivative of the current. Here's an easier way to do it, and here's how the solutions also kind of find it. As we know, the equation that we're going to find, right, the solution we're going to find, it's going to be in this form right over here, right? So that's going to be our current. And as you know, the inductor voltage, right, is equal to L times the derivative of the current, right? So all we need to do is find the derivative of this thing. It's a little complicated. I'm not gonna do the whole derivation right now. I'm just gonna give it to you as it is. You can probably just write this down on your cheat sheet. It'll help you a lot. But remember, it's L times that derivative, right? So what's the derivative? Well, it's negative alpha B1 plus omega D B2. All right, we have that times cosine omega dt, all right, plus negative alpha b2 minus omega d b1 sine omega d, oh boy, t, all of this times e to the negative alpha t. All right, so what we did is we took the inductance, we multiplied it by the derivative of the current, and that gives us our voltage, right? And yeah, again, we didn't find this derivative. I'm just giving it to you because, you know, you could just write it down in your cheat sheet to make it easier. But yeah, now why am I doing all of this? Well, if you notice, this equation already has b1 and b2 in it, right? And we know all the other variables. So we can use this equation to find our b2. So here's what we're going to do, actually. First of all, we only need to find it at a certain point, right? We only need VL at 0, right? So what is VL at 0? Well, that's just 0. And how do we know that? From the first part, right? VC and VL are going to be the same thing since they're in parallel, right? So this voltage is going to be the same as this voltage, right? So we already found that that's 0, which means that now we can use that to find B2. But how are we going to do that? Well, first of all, L times whatever, right? L times anything, right? We divide both sides by L, right? So then we can get rid of the L too. So we could literally just say, you know, get rid of this L and just use this part and say that this 0 is equal to, oh boy. Here's the thing. It's a big equation. We don't have to write this entire thing down, though, because let's think about this logically. All right, we have two boxes over here. This is the cosine, and this is the sine. All right, we're at time equals 0, right? So this sine is going to go to 0, which means this whole thing is also going to go to 0. So we can literally just get rid of this for a second. This time is going to go to 0, which means this whole thing is going to go to 1, right? So we could get rid of this. We can get rid of this. All right, what do we have left? We just have this phrase over here, right? And this is also going to be 0, which means this whole thing is going to go to 1, right? So all we're looking for here is this, because we also got rid of this, right? So all we're looking for is this over here. That's how you can use the zeros to simplify it a lot. Okay, cool. This is a lot friendlier of an equation to solve if you do some moving stuff around. Let's do that really fast to get B2 alone. So we know that alpha B1 is equal to omega B2, right? And then we just divide. So alpha over omega D B1 is equal to B2, right? So now that we're here, we already know what B1 is. So we can easily find B2 from this relationship. We can just say, what was our alpha and omega? D, okay, so 50K over this number. I'm not going to write it down. You can sub it in on a calculator, right? I'm just going to give you the answer. It's pretty straightforward. These two times negative 10, right? That's our B1, is equal to what? What's it equal to? Negative 2.582. All right, I rounded it off, but this is our B2. All right, cool. So now we have our B1, we have our B2, we have our this thing, right? So we're done. So we already have the equation now for IL of t, right? Again, referencing off the cheat sheet, IL of t when it's underdamped is equal to B1, right? What's B1 again? B1 is negative 10 cosine omega d t plus, or in this case, it's B2, right? So it'd actually be minus 2.582 sine omega dt times e to the negative alpha t, right? So here's the thing. Are we done? No. We can't just use this because we also need to add on our forced solution, right? So what's our forced solution again? Well, if you look at here, as I of L goes to infinity, it's 10, right? So our forced solution means we just add on 10. And yeah, there is our IL of t. So we can just take this and put it in to our first answer. And we also need to clarify what these terms are because we can't just leave these as variables, right? So we can even write down that alpha is equal to 50k and WT is equal to 193,649.17, right? Now we have our completed equation. And one thing you'll notice in the solutions is that it uses the exact same equation, but it simplifies it a little. It moves this 10 to the front. It takes the negative out of this. But the solutions in this have the same answer. So yeah, here's the thing. We can't just say that, though, because we need to clarify that all of this, right? So let's put parentheses around it. All of this happens when t is in between, this and 20 microseconds. All right, because remember, we're doing a piecewise. This function that we found only holds before 20 microseconds, right? Okay, so while we're still here, right, while we're still before 20 microseconds, let's skip this for a second and just, find the voltage across the capacitor at that same time. So, because that'll be easy since we already have this work done. So if you look at it, the voltage across this and this are the same thing, right? Which means we just need to find the voltage into the inductor. Again, we have our equation for that voltage into the inductor. It's right here. And we could just totally use that in our equation for the capacitor. But we could also simplify it a little just to make it easier. So let's take a look at that. How can we simplify this? Well, if you look inside here, this thing and this thing are the same thing, right? And what we already decided is that this is equal to 0. We already decided that. So we know that this point has to be equal to 0, which means that gets rid of that gets rid of that. So all we need are L, and we need this part, okay? So let's, honestly, I'm just going to drag it over since we already have it written out. And let's just get rid of those parts. So if we move the equation here, we know that, and we can actually, change this to say V of C. And this is just going to be equal to, getting rid of this stuff because this all goes to 0 anyways, right? Getting rid of this sign. And then closing in everything. This is our answer, right? Now, we could, leave it like this and throw the numbers on the outside, or we could simplify it a little. This stuff can be simplified since we know the numbers already. So we can also set this equal to, this actually turns into, if you plug it into your calculator, it turns into 51.640 volts, right? So we have that times sine omega dt e to the negative alpha t. So we know that this is our equation, right? This is the answer. So we can literally just take this and copy it and move it over. We might have to, the solutions don't do this, but I mean, it would be good practice to redefine, alpha and omega d over here, since technically we don't have them defined here. I guess the solutions don't do it, so you don't really need to, all right? And again, this is part of our piecewise, so we're going to say this is between t and 20 microseconds. All right, cool. Now let's find out what happens after 20 microseconds. What do we put in these two blanks? Well, taking another look at the circuit, now we know that the gate has opened, right? So what does that mean? That means that this thing becomes an open circuit, right? So we can get rid of that. What does that mean? Well, that means that there's no connection to this capacitor over here, right? So honestly, this goes away too. Okay, so now that we've, cleared up the circuit, what do we have left over here? Well, this is another simple parallel first order circuit with an inductor, right? We have that on our cheat sheet. Where do we have it? Right here, right? So we have our inductor, we have our resistance, right? We just need to get it into this form. But once we get into this form, we can use these equations, right? So let's get into the right form. We're just going to need to source transform this. So let's take this and say, source transforming it, we can say this is equal to, the voltage is equal to I times R, so 10 times 10, which would be 100 volts, right? Go like this, add in our resistor here. The resistor is going to be 10 ohms, and then we have our inductor. Go down here, connect it, boom, boom. All right, so now we know that we have it in the right form, so we can literally just use this equation right over here and say, what was the equation? Yeah, ILT is equal to VS over R plus IL0 minus VS over R e to the negative R, TRL. Right, so that's our equation. Here's the thing, keep this in mind. We are not at time equals 0, right? That's not where we are. So this, and this need to be updated. Why? Because we're actually at 20 microseconds. So to get the equation in the right spot, what we actually need to do is take this t and say it's t minus 20 microseconds. All right, that's important. Plus, we need to find this term I of L at 0. But again, we're not finding it at 0. We're finding it at 20 microseconds, right? Because that's where we are right now. So this is the equation we need to fill in. Again, V is 100, R is 10, right? So 10 plus I of L at 20 micro. What is that? What is I of L at 20 micro? Well, if you notice, we actually have an equation written right here for it, right? So we can actually plug in 20 micro amps into that equation, or sorry, 20 microseconds into that equation. And what that'll give us is that'll give us the number, and I'm just going to tell you it, you can plug it in, find it out for yourself, 13.372 amps minus another 10 amps, right, from that V over R times E to the t minus 20 microseconds. R, what's R in our case? It's 10, right? 10 over 20 micro, this is 25. Sorry, 25 microhenries, right? So we have this, we can simplify it a little, right? That the inside of this becomes 3.372 amps, right? Times E to the t minus 20, right? 10 over 25. But there's our answer. So what you'll notice is the way this number is represented in the solutions is a little different, but technically if you do the math, it's the exact same number as the solution. So yeah, we can just copy this and move it in. And there we go. Now we have I of L for all the numbers, right? We just need to say what this is. This is when t is greater than or equal to 20 microseconds. Right, now we have one thing left. So now how do we find this? The voltage of the capacitor over time when t is greater than 20 microseconds. How do we find that? Well, again, these are parallel, right? So it's just going to be whatever voltage is in the inductor. But one thing to keep in mind is that when we're finding this, we don't have to consider how this changes, right? Because it's not going to change. Once this gate is opened, right, this becomes, cut off from the circuit, right? Which means that this voltage is not going to change at all. It's going to stay constant. And we already have an equation that tells us what that voltage is, right? It's right here, right? This equation. So what we can do is we can plug in the numbers, and I'm not going to do it again because, you know, you have a calculator, you can do it on your own. But the answer to that would be negative 12.688 volts. All right, and yeah, that's our answer.